Hello and welcome to my video presentation for this year's virtual ISPRS conference. My name is Gehrung, and my talk today is about efficient tour planning for a measurement vehicle by combining next best view and traveling salesman. I would like to start by giving a brief introduction into the topic and our motivation for this contribution before I move on to present our method for efficient tour planning. The main part is about the algorithm that we designed to solve the tour planning problem in order to support change detection in large environments. This part also includes experiments and results. And finally, I'll give you an insight into the next steps and a general conclusion. Change detection is currently a major topic in various fields of research such as city modeling and autonomous driving. Both require change detection on a large scale, for example to keep city models and maps up to date. Recording such datasets is a time-consuming task. The two examples below should illustrate this. On average, the measurement vehicle used to record the dataset generates about 2.5 billion range measurements every 30 minutes. Post-processing these large amounts of data requires a lot of computational resources. And that also not only part of the data is really of interest. A straightforward solution would be to focus on areas relevant for the task at hand. In order to do this efficiently, a method for tour planning between all points of interest is required. In the next few minutes, I would like to present our solution to this problem. However, before I present our method, I would like to discuss the constraints we have imposed to keep the problem simple to solve from an algorithmic point of view. The goal is to observe a given set of points of interest. To observe a point, the vehicle has to be placed in the direct vicinity or at a location where it is able to see said point of interest. This is also what we call indirect viewpoints. For the sake of simplicity, drive-bys do not count as observations. The resulting tour has to be as short as possible and should visit every point of interest exactly once, as it is shown here. Please keep in mind that these constraints mentioned here are crucial to ensure a simple algorithmic solution within this proof of concept. In order to determine the indirect points of view mentioned before, an occupancy grid is used to determine the area that is visible from each point of view. A candidate for an indirect viewpoint is found whenever two or more of these areas overlap. The green points in the image symbolize points of interest. The red point is an indirect viewpoint that allows to observe both points of interest. In addition to the indirect viewpoints, a so-called visibility matrix is determined. It describes which points of interest can be seen from other points of interest or indirect viewpoints. The weight vector is the sum of a rows of the visibility matrix and is used later on to solve the next best view problem. For the full example shown below, the visibility matrix and weight vector look like this. Our algorithm utilizes a sorted list that contains all points of interest as well as the indirect viewpoints. The list is sorted by a score that encodes the cost-benefit ratio of the point, which is the associated rate from the weight vector divided by the distance to the last point in the tour. The first step in the algorithm is adding the start point to the tour. At the beginning of each iteration, the list is initialized with all remaining points. At the start of the algorithm, that's all points. Then the point with the best score is determined. The distance part of the score is estimated by the Euclidean distance if no path is known. If no path is known, it is calculated using hybrid A star and the point is reinserted into the list, since after the length of the path is known, it may not be the point with the best score anymore. If the path is known, that means that it is the point with the best score, it is added to the tour. Also, the weight vector is updated. More about that in the next slide. This process is repeated until there are no points left. If this is the case, the start point is added again to the tour and the algorithm terminates. This example shows a step-by-step execution of the algorithm. After selecting the point with the best score, all points that can see it are determined using the visibility matrix, and the corresponding columns are subtracted from the weight vector. This is the aforementioned update of the weight vector. The purpose of this is to decrease the value of the other candidates, since some of them can see already observed points. In the first step, 2 out of 4 points of interest have been observed. After the second step, all points of interest have been observed. This is reflected by the weights vector, since there are no points left that would be worth visiting. The result is a tour that visits 2 indirect viewpoints and observes all points of interest. Our methods have been evaluated with the 2 synthetic datasets shown below. For each dataset, a ground truth has been created by applying an exhaustive search. The optimal tour found by the search is compared to the result of our method. The vehicle itself is simulated by a 3-dimensional bounding box. The path finding is implemented quite simple. Per step, the vehicle can move either forwards or backwards in one of 5 directions. The distance covered per step is predefined. The results of our approach are compared with the ground truth in terms of optimality and runtime. The tour quality is also discussed. The evaluation has yielded the following results. A comparison with the ground truth shows that our method was able to determine a near optimal tour for our simple dataset. In the diagram below, the tour selected by our approach is symbolized by the red line. The blue line shows the length for any valid tour of the ground truth. It should be noted, however, that the tour chosen seems more intuitive than the optimal one. In case of the complex dataset, our approach was able to determine the optimal tour. The tour also looks intuitive to the human observer. In terms of runtime, our approach required 3 minutes to solve a simple dataset and about 10 minutes more to solve a complex dataset. A closer examination of the runtime leads to the conclusion that path planning is a major bottleneck, and the actual runtime of our algorithm is neglectable for both datasets. It was also concluded that the vehicle model and the path planning algorithm have a large influence both on the results as well as on the ground truth. This includes factors like the shape and dimension of the bounding box, the initial orientation, speed and maximum steering angle of the vehicle, as well as additional path planning heuristics. We've shown a simple algorithm that is able to generate a tour for an informed exploration of a given environment. We demonstrated the algorithm on 2 synthetic datasets. The evaluation showed that the problem at hand can be solved in reasonable good time and with close to optimal solutions in a lab environment. Path planning has been determined as the bottleneck both in terms of runtime and performance. In order to apply said algorithm to a real environment, path planning must be changed for a faster version. Also, an expansion of the rules is in order, especially with regard to handling observations by drive-by maneuvers. And last but not least, real-world problems need to be identified and solved. This brings me to the end of my presentation. I recommend that you have a look at our paper in order to find more information. This includes a theoretical background for both next best view as well as traveling salesman, and a more detailed description of our algorithm, its properties, and of course the evaluation. Also, feel free to contact me by email if you have any questions. Thank you very much and have a good time.